at its core, machine learning is all about predicting. All machine learning techniques aim to predict certain event based on data known from the past. We are going to do that today regarding a healthcare use case. We are going to predict what is the risk of death from heart failure in a patient population regarding several patient conditions. We are going to do that using generalized linear models, which is a foundational machine learning technique that can help in this type of classification problem. We are going to understand what this technique does under the hood and what are the characteristics that your data should have in order you can apply this technique. Follow me to the demo. For running this demo, I want to invite you to go to teradata.com/experience. I will put a link to that in the description of the video. Then create an account. It's very easy and it is free. Once you have your account and you confirm your email, you will be able to log in at clearscape.teradata.com, sign in. I already have my account here and you're going to see this dashboard. You need to have an environment. I already have one here. Remember, when you create an environment, you are going to be asked a password for that environment. Keep note of that. You are going to need it later. Then you click on Run Demos. This will take you to a Jupyter Lab environment. Go to Use Cases and then navigate to Heart Failure Prediction. Open the notebook and you will see the demo that we are going to be working with. For this demo, I want you to pay special attention to what a generalized linear model is and what it is doing. A generalized linear model is taking a set of independent variables and finding a function that, when fed these different variables with different values, can give us accurate predictions of a dependent variable. The model does this by iterating and adjusting the parameters of the functions that the model itself is coming with in several iterations. Since this type of model requires that all of the independent variables are numeric and in a similar scale, you have several data preparation steps that need to be performed before creating the model. In Teradata, you can make this type of analysis very, very fast at scale. Let's get to it. We are going to start by importing all the required libraries. We have some system imports. We have the Teradata related imports, especially valid, which we are going to use a lot in this demo. Now that all our libraries are installed, we are going to connect to Teradata Advantage. For this, we need our password that we set when we started our environment. For getting the data for the demo, we can get it in two ways. We can either get it as foreign tables. That means that the data will stay where the data is stored in object storage, but also we can upload this to the Teradata Advantage environment, which will allow us to run the data faster. The native object storage capabilities of Teradata allows us to either create foreign tables that point to an object storage in any cloud provider, be it Google Cloud or AWS or Azure, or very quickly ingest the data into our Teradata Advantage environment. I will choose this latter option, which is the one that is activated by default. Now we're going to proceed to explore the data. As mentioned, this is a synthetic data set that we built based on some healthcare information that is related to patients that have certain heart failure and whether the patient unfortunately died or not. This is a synthetic data set, so what we are going to be covering in this demo is how to create a model based on this data. The results are going to make sense for the most part, but remember, this is a simulated data set, so the results of the model are not very important as to the process and how you create this model. You learn how this model works, and also how you can preprocess the data for this type of model very easily with the features that Teradata Clear Escape Analytics offers. So let's load our data, which we have right now in a table in our database, to a data frame. And let's start by checking out the shape. As you can see here, we have 1,000 records. The data set is very small, and we have several columns. Of course, we have an ID to identify the patient. Then we have the outcome, whether the patient died or not. And we have several independent variables that we want to analyze what is their weight as predicting whether a patient is in a very high risk of dying or not from a heart failure. For this, we have the following independent variables. We have, of course, the length of stay, so how long the patient stayed in the hospital, the age of the patient, the gender, whether the patient has cancer, whether the patient has a CAPG, which is a heart surgery, where they have a CRT, defibrillation, other diseases like dementia, diabetes, hypertension, and so on and so forth. We are going to analyze all of these independent variables as to what are their weights for a specific patient to have a very high risk of death according to the data that we have. As seen in the data, we have some variables that are just a specific quantity of days stay in the hospital or the quantity of years old that this specific patient is. These type of variables are purely numeric, and we can prepare some statistical analysis to normalize them. In order, we are comparing apples to apples when we are building our regression model. We have other type of variables that are very similar to a Boolean condition, either true or false. And these are the ones related to other diseases such as cancer, dementia, or diabetes, or the medical procedures such as the CAPG. These have a 1 if the patient has had that procedure or has this disease, or 0 if the patient doesn't. These are very easy to put into a model because they are actually all in the same scale. It's either yes or no. Very easy to model. We don't need to normalize them. Those are great. But we have other variables where we have certain categories. For example, we have the quintile of income of this patient. So what is the income level and what that income level means? We are going to transform this one into another type of encoding, which we call one-hot encoding. So basically what we are going to have is a column that will represent each of these values from 1 to 5. Those column titles might tell us what that number specifically means. And then if the patient, for example, is in the quintile 5, we are going to say, okay, this patient is in a certain socioeconomical status, and the same goes for the ethnic group. As you see, what we are going to perform in our data preparation is normalization. For the values that are purely numerical, we are going to apply statistical normalization so they are in the same scale. For the ones that are categorical values, we are going to apply one-hot encoding to make them Boolean statements. And you might be wondering why is this important? Is because for building this analysis, it is very important that we are comparing apples to apples to have a better model. Let's check it out here. And we have several bins of fields, as you can see here. We have num(x), those are the numerical data that we are going to transform through statistical processes. We have the categorical data, which we are going to encode through one-hot encoding. So the title of the columns tell us what that specific value means, and the value is going to be just a 0 or 1. And we have the binaries, which are the ones that are very similar to Boolean statements. that we are just going to leave alone. Of course, we also have our ID column that identifies the patient. For performing all of these transformations, we are going to use the functionality of the Teradata ML valid library, which makes it very, very easy. We just need to define what are the transformations that we want to perform, and the library is going to make it for us. Take as an example the categorical transformations. We are going to transform the quintile information, where the value 1 means that that customer is at the top of the ladder regarding socioeconomical status, and the value 5 means that it's in the lower status. So right now, these are going to be new columns that we are going to create, and whether the patient is or not in that specific bucket is going to be signaled by a 0 or a 1. We are going to do the same for gender, male and female, and we're going to do the same for the ethnicity, which we have here as with the following encodings. That is regarding the categorical data. For the numerical values, we are going to perform a statistical transformation, and that's the z-score. We are going to apply for the columns that we define as numerical. The output columns are going to be the same. And of course, we want to deal with the non-available numbers, the ones that are null. And for that, we are going to utilize another function in Teradata ML valid library that is called fillNA, which will assign a value to those and apply the z-score correspondingly. And for the rest of the columns, the ones that were already binary or Boolean, as we were calling them before, we just retain them. They are already in the state that we want them for working with them. Now let's run this code so we can prepare our data. Here, after we created all of our definitions in these dictionaries that we created before, we are going to perform our transformations with valid. This is the part that is very interesting. So we are going to use from Teradata ML valid, the transform method, and we are going to store the results in this data frame that is called df transform. This is very easy. We just define what is the data that we're going to be using, which is heart failure. We are going to define that for the numerical values, which is what we define here in ZS, we are going to apply z-score. And of course, included in that is the dealing with the non-available numbers or null. Then we are going to apply one-hot encoding to the buckets that we define here. So we have precisely defined what are the column titles of those one-hot encoded columns, and one-hot encoding just means that we are encoding with a 0 or a 1, so we are making them binary. Then the rest of the columns we retain, which we define already in this code over here, where it was, yeah, here it is. And then we define an index and a key. Let's proceed to execute the code. Once the transformations are performed, we can proceed to store them in database, and we can see the results now. Here we have the values, our numerical values already statistically processed. All of these that were in very different scales right now are in a similar scale, which is very good for our model. We also have our one-hot encoded columns, which are related to ethnicity and socioeconomic level. We can then proceed to split the data, and we have a function for that that is called train test split in Teradata ML that allows us to assign a column inside the data that will mark that specific data point as train or not. And we are going to assign it with a 75% of likelihood of a data point being for the training set and 25% for the testing set. And we do that with this code. After we apply it, we are going to drop the columns that have been created to mark them as train or test, and we are going to store the train data set in a specific data frame and the test data set in another data frame. We transfer two tables to persist them. Of course, the training set is 7.500 and the testing set is 2.500, which we have already certain knowledge because we have 1,000 data points. 75-25 division will look like this. And what we are going to do right now is to allow the Teradata ML generalized linear model generate a model for us based on our data that will be able to predict, based on all of the independent variables, what is the risk of a patient dying from a heart failure or not. The general linear model takes the following parameters. We have the data in which we are going to train the model. We have the definition of what columns we are going to use to train the model, which we have from the beginning to the end of our specific training set, except, of course, from the ID and for the death column, which is what we are trying to predict. Then the response column, which is death. The family is binomial because we are trying to classify. Is going to predict whether death or not death with a 1 over 0 correspondingly. The batch size, iteration maximum, lambda, alpha, and all of these other parameters, these are already set for us in this demo. But for understanding what they do and when you might want to tweak them, you have to understand what this model is doing. This model is trying to find a function which, taking as an input the values of the independent variables, all of those variables that we have discussed before, will output one result, which is a 0 or 1 in the column for death. We don't know what that function is, and actually no one knows. The function is hidden in the data. So what the model is going to do is taking the data in certain batches, so that's the batch size here, and we'll try to take all the individual independent variables, pose a certain function that the model will come up, and see if the predictions are correct regarding the predicted column. If the predictions are not correct, the model will apply a certain adjustment to the parameters of the function it prepared. There is another function that helps the model to do this. It's a loss function that tells the model whether the model have to move certain parameters in one direction or another, and then the model just goes with another iteration to see if there is an improvement in its prediction capabilities. And we are going to do that up to 100 times in this case. These parameters here help the model perform certain adjustments. Description of what these do in detail is outside of the scope of this demo, but there's a lot of documentation for this. I might put some materials in the description of the video. This initial ETA is how much the model will update its parameters initially. What is usually called the learning rate is how aggressively the model goes for updating those parameters that will tweak the function to actually give us the prediction. And the learning rate means that after the model runs one time with this, we'll take this as a baseline, and then it might try to optimize that learning rate accordingly to what the predictions are according to the data. What you have to remember is that the model is just trying to come up with a function that, when feed the independent variables, comes with a value for the predicted dependent variable, either 0 or 1. that is correct according to the data that the model knows. And we'll try to do that 100 times, though if it finds that got to a certain optimal result before reaching the 100 iterations, it will just stop there. So let's do it and check the result. This result is just the value of each parameter in the function. So it's basically letting us know how much each of these parameters influence that predicted value that we have. So it's our value for the function that the model came about after being created. Pretty cool and quite fast, as you have noticed. Now, let's visualize a little bit of the results. And here we have, as expected, the values for the age and length of state heavily influence death. We have also arrhythmias and the CAPG, a little bit related to the death chance, but also negatively correlated. So that's a little bit weird, but there might be explanations on that. Maybe someone that has an arrhythmia already has some treatment being seen by a cardiologist, and the same goes with this CAPG. But of course, this is a synthetic data set, so we should not read a lot on the results. We are analyzing the method on how to get to these results here, not as much the results themselves. And of course, Teradata also offers you the functionality to have this model that we just created make predictions and check how good those predictions are as related to the actual data that the model has not seen. So we're going to use our test data set here, and we are going to perform our evaluation. We are going to get the output of that evaluation. And what we are doing here is basically making the prediction, and we have what are the probabilities that our model assigned for that patient to die or not die, and we assign the value of our prediction according to these probabilities, and we have the ground truth here. Then we can also visualize the results of our predictions, a confusion matrix, which is a common way of measuring the accuracy of machine learning models. What this confusion matrix is telling us is that of the total of non-death patients, the whole universe of those is 79 plus 52. 79 we captured, 52 we didn't. So we have 131 non-death cases. So we have about 60% of non-death classified correctly, and about 39 missed. And conversely, the same goes for the death cases. In summary, machine learning can be used in a lot of different scenarios. The generalized linear model is very handy to predict multivariate regression along big data sets. What it does is basically take all of these independent variables and build a function that is able to take those values to predict a dependent variable. This type of analysis could be very useful in healthcare, as we have shown in this demo, and you can run this very efficiently and at scale with the Teradata ML library. I hope that you have enjoyed this demo. See you in the next one. This is Daniel, and I hope you have a great day.